All right, welcome back. Let's look at this example here. So we have a 5 kilogram box sitting on a rough surface. And we are given in the diagram the coefficients of static friction, 0.6, and kinetic friction, 0.4. So, so the box sitting on a rough surface is suddenly being pushed by a 35 Newton force at an angle of 20 degrees with respect to horizontal. Our goal will be to identify all forces acting on the box and draw the free body diagram. All right, so let's do this and then continue with the rest of the problem. Okay, so the first thing you want to do here, again, do the free body diagram by identifying all the agents. And you can see, right, agent will be some kind of, person maybe pushing or pulling with this 35 newtons. There's Earth exerting gravitational force and the surface, normal force and friction perpendicular and parallel to the surface as well. That means we have three agents, person, probably pushing and pulling, Earth, and the surface. So if I do the free body diagram, I will then take my object to be at the center as a particle. And then the forces acting will be the first agent. So this will be then applied force acting at 20 degrees. Then Earth exerting gravitational force straight down, normal force straight up, perpendicular to the surface, and then the friction. And this friction then, at this point, we don't know if it's kinetic or static friction. We're going to figure out that in a minute. But we know that there is a friction because it's a rough surface, and we have a coefficient for both kinetic and static frictions. Okay, so this will be then the free body diagram. Now, the next question is that, is the applied force strong enough to make the box move? Okay, now, what we know here is this, right? So if I consider this to be step one, and then step two will be then to the table. It will allow me to kind of like, let's say, what do I have in an x direction as a net force, and if that net force in x direction strong enough to basically overcome the friction force. All right, so we have forces here. So I have applied force. Let's put like applied, put like A for applied. And I have friction force, I have normal force, and I have then the gravitational force. Okay. So all of them together is the net force. But again, we have to break down into components. So X component, Y component. All right, so I can see that again, applied force is, if I break this down, it will be applied force in the X direction, applied force in the Y direction. If I break them down, again, I have a right triangle theta with respect to the X axis, which means that my components are given as FA cosine of theta A, FA sine of theta A for then the Y component. First quadrant, so plus plus. Friction, on the other hand, is the one-dimensional force, and it's acting in a negative X direction, has no Y component. Normal, again, one-dimensional, no X component, Y component straight up, so positive. And weight has no X component, it's in a Y direction, straight down, so negative mg. And I know one thing, that in Y direction, regardless what happens, because it's going to be moving just from this initial to final position along the horizontal axis, in a Y direction, all the forces cancel. But in the X direction, at this point, I don't know, right? Is the net force zero or not? We're going to have to calculate and see. Okay. So, but this allows us to set up the equations. So you can write equation one, which is in step three, is nothing but the sum of horizontal forces, which is in the second column. So I can see then I have what I have is just FA cosine theta A minus friction. And this will be then equals mass times acceleration. So if the force is balanced, then the acceleration is zero. You're in equilibrium. If force is not balanced, that means applied force is strong enough, then you get acceleration and object will be then accelerating. Now, equation two then will be net force. So like this is equation one, net horizontal force. Equation two, net vertical forces. So this will be then FA sine of theta A plus normal force minus mg equals 0. Now, the idea is this, right? So we can see that not applied force, but the horizontal component of the applied force is the one that is going to be acting against friction, right? Try to push the box in a horizontal direction. So friction going to be opposing only the x component. And I can calculate that, right? So I can calculate what this x component is. So FA x is equals to FA cosine theta A. This is 35 newtons times cosine of 20 degrees. So let's calculate that applied force. Well, it is 33 newtons roughly. Okay. Now, is this strong enough to overcome static friction force? Well, we don't know yet, but we have an equation for the maximum static friction. Remember, static friction is adjustable force. It can adjust itself to match the applied force, but to a certain degree, right? That means it has a maximum value that cannot go above. That maximum value is given as coefficient of static friction times normal force. And coefficient of static friction I'm given as 0.6. That means if I know what normal force is, I can plug in and calculate the maximum static friction force. If the maximum static friction force is greater than applied force in the x direction, that means the horizontal component of that, object will be in equilibrium. That means that, it will not move. But if the opposite is true, then obviously the object will then start accelerating, the friction will become kinetic, and then we can calculate acceleration from that. So let's do that, right? So we can see that equation 2 allows me to calculate normal force using that equation. If I rearrange, normal force is equal to then mg minus fa sine of theta. And I can come back here and see that box is 5 kilogram. And I can just then do 5 kilograms times 9.8 meter per second square minus then 35 newtons times sine of 20 degrees. Okay, so normal force is equals to, so 5 times 9.8 is 49 newtons minus, so 35 times sine of 20. This is about 12 newtons. That means what I have here is 49 minus 12, 37 newtons. That's my normal force. Remember, applied force is not fighting against normal force. So I have to take this and move it here. So then the 37 newtons. And the static friction force will be then 0.6 times normal force. So it is 22.2 newtons, which means my applied force is significantly, stronger than the static maximum force. So my object will not stay at rest. It will then accelerate. Okay, that means coming back and answering one of the questions, right? For part B, is the applied force strong enough? Yes, it is strong enough. And we know that because we can calculate it and compare where this is 33 newtons, where the static maximum force is only 22.2. Then you can write the next part is that find the net horizontal forces and then net vertical forces, acceleration, and displacement if it moves in for 4 seconds. So let's go ahead and do that. That means equation 1 and 2 can already allow me to do that, right? So equation 1, net force in x direction will be, FA cosine theta A minus friction. But here's the thing, right? If I know that it is moving, then I don't use static friction anymore. I have to now use kinetic friction. Because as soon as you have applied force stronger than the static friction force, for the net force, you have to use kinetic friction to calculate some kind of non-zero net force. Because remember, right, static friction only acting as long as it's not moving and it balances the applied force. Well, which means that here I can calculate this to be 33 newtons. But kinetic friction, I have to come back and calculate, which will be then in the picture here, 0.4. So 0.4 times normal force. So 0.4 times 37 newtons, which is the normal force. So equals, so 33 newtons minus 0.4 times 37. We end up with 14.8, just round it to, let's say, 15 newtons. So 33 minus 15, we get 18 newtons of the horizontal net force. And obviously, vertical net force, we know it's already 0, so we have that as well. Well, one of the things we have then is that, let's wax the answers. So then for the acceleration, obviously, if the net force in the y direction is 0, vertical acceleration is 0. But then horizontal net force produces acceleration because it's non-zero. So we can calculate that acceleration as net horizontal force divided by mass. So this is then 18 newtons divided by 5 kilograms. So we can calculate this to be 3.6 meter per second squared. Okay. Then this will be then the acceleration. And what we wanted to get for the last part is the displacement when it goes from initial position to final position. Okay. All right, so we can calculate that as well because we are given that it starts from rest. So initial velocity is 0. Time was given as 4 seconds. Acceleration now 3.6 meter per second square. And remembering that kinematic 2 equation will give us then final velocity independent equation to solve for displacement. X final equals X initial plus V initial T plus 1/2 AT squared. We can assume that this is 0, this is 0, then X final is equals to 1/2, 3.6 meter per second squared times the time of 4 seconds. Then squaring that. That means we can calculate the displacement. Which will be then 28.8. So we can just put like 29, rounded to 29 meters as the displacement. All right, so again, to summarize what we did, we started with free body diagram, identifying all the agents and the forces acting on the object. Then we did the force table where we organized everything, all the forces in terms of their components, correct signs and everything, which then allowed us to set up equations 1 and 2. Equations 1 and 2 are important because those are the equations for the net force. It told us that in order for me to calculate if the object will change its motion or not when it's being pushed by 35 Newton force, I needed to find X component of the applied force and compare it to the maximum static friction. And that's what we did, right? So we calculated the X component of the normal force, which is 33 Newtons. Then to find maximum static friction force, we had to use this equation 2 to calculate the normal force and then calculate static friction force because that's a coefficient of static friction times normal force. And we end up with 22 newtons, which is significantly less than applied force. So the conclusion was that the object will accelerate, start accelerating, changing its motion. In that case, as soon as we want to then calculate the net force, after learning that the object will accelerate, we would have to use kinetic friction rather than static friction, which has the same equation, but uses coefficient of kinetic friction rather than static friction. And coefficient of kinetic friction always less than coefficient of static friction. That means we had 15 newtons of kinetic friction acting against the applied force rather than 22, because as soon as the object being applied by stronger force than the static friction force, it will then friction right away change to kinetic. Anyways, we use that to calculate acceleration and then move to kinematics and solve then the displacement. We could also solve other things like final velocity and things like that, but the question didn't ask us for that. Right, so then this will then pretty much be, the full solution for this problem.